In this video we're going to be looking at the non-inverting amplifier using an op-amp. So in this case the input is applied to the non-inverting terminal. So the easiest way to actually remember this when you're looking at the circuits is that if it's applied to the positive terminal then it's non-inverting, and if it's applied to the negative terminal then it is an inverting amplifier. As before, we apply a proportion or a fraction of our output back to the inverting terminal. So we have negative feedback once again. In this circuit, and we have V in, V out with two resistors. The resistor in the feedback network I normally call RF, and in this case I'm going to use RI again for the second resistor, and our task is to find AVCL, or the closed loop voltage gain for this particular circuit. Noting once again AOL for the particular op-amp that we've chosen. Now we saw previously in the inverting amplifier example that IM was equal to 0. Nothing changes in this particular circuit here, so that IP is going to equal to 0 and IN is going to be equal to 0. Right, so we still use those ideal approximations. So from that, what we can do is we can say that the current through II will be equal to the current via IF. Okay, and I'll just draw that arrow a little better. Right, so all the current's flowing this way because no current is flowing into the op-amp. So given that scenario, we can substitute in the known components for this configuration. So the current II will be equal to Vn minus 0 to ground over Ri, which will be equal to Vout minus Vn over Rf. So we get the final expression here, Vn over Ri is equal to Vout minus Vn over Rf. Now, from the original expression for our differential amplifier, which was Vout is equal to the open loop gain times the difference in voltage between the inputs and the virtual short, which comes from this expression, we know that Vn is equal to Vp when we take that virtual short approximation. So Vn here is actually equal to Vp with a virtual short, and therefore we can substitute into this expression Vin for Vn. So Vn being the same as obviously Vp, this is Vn here, those two are equal according to the virtual short, is equal to Vout minus Vn over Rf. And if we rearrange that and solve it just like we did for the inverting amplifier, we will see that the closed loop voltage gain is equal to, same expression always for the amplifier, output voltage over input voltage, which in this case is equal to 1 plus Rf over Ri. Right, so just take note that with that 1 there, the closed loop voltage gain must always be greater than 1. Right, well, yeah, always greater than 1 approximately, or at the very minimum 1 itself. So there's no attenuation in this configuration. So just that again, right, we know that the current here, In, is equal to 0 from the ideal approximation. Therefore all the current flow IF will be going through II. Voltage drop across Ri divided by Ri gives us the current through it. Voltage drop across Rf divided by Rf gets the current through that resistor. Equate those based on that expression. From the virtual short, we know that Vn, the voltage at this point here, is equal to Vp. because there's effectively a short between these two here, Vp being the same as Vin. Substitute, rearrange here for closed loop voltage gain, we get this expression here. Now, there is another way that we could look at this particular circuit. We could look at it from the negative feedback viewpoint or analogy. We'll take an analogy. So just like we saw when we did the analysis of the negative feedback down here, alright, where we've got our op-amp here with its fraction of the output applied and subtracted from the input, we saw the expression here for closed loop gain was equal to 1 over beta. Alright, so we'll draw this again. So AOL with a fraction taken back and subtracted from the input, and we get closed loop gain was equal to, approximately equal to 1 over beta. Now, we can apply that to the circuit up here, because we can see that the feedback, okay, the fraction applied, is merely a voltage divider in this circuit, alright, where the voltage Vn is the voltage across this resistor here. So let's see how that would look. Alright, noting that beta is merely a resistor divider, which for our circuit is the voltage across Ri. Okay, and remember beta is just the fraction. So the fraction taken of the output subtracted from the input. So we can say it is equal to this expression here. And using this expression up here, we can say that closed loop gain is equal to 1 over beta, which is equal to 1 over Ri over Rf plus Ri. And when you flip all that over, you get Ri plus Rf over Ri, which equals 1 plus Rf over Ri. And you'll note it's the same as we solved for using the current and voltage laws associated with that circuit. So using a feedback analogy with negative feedback, we can also get to the same approximate gain.